Thank you very much. Thanks, James. Ankit, well, not here. Yeah, thanks for inviting me. I think I'm a little bit of an outlier here because the most powerful laser I know is this one. So what I'm going to tell you is about quantum materials at the micron scale. And before I actually jump into this, I'm actually going to thank everybody because that was involved in this. We do microstructuring, but we have lots of help from people that do crystal growth, so mainly Andy McKenzie's group in Dresden for providing materials. I'm from Philip Moll's group, so we just moved from EPFL to Hamburg, and so we're the latest addition to the Max Planck Institute, and now postdoc Junyun Go. And for the optical measurements, we mainly work together with Atach and Ken Birch. That really helped us in this because, as I said, I'm really no expert. But I want to flash that first because what I'm going to tell you is a little bit different to what we heard so far through the workshop. And so I would encourage you to ask me questions whenever they come up because I'd rather not tell you everything I want to tell you and really make sure you understand what I tell you. The things that we heard mostly, or the materials that we mostly heard about, are layered materials in the sense of graphene always came up, right? So you have something that's finite size confined because you grow a thin film or you have an atomically thin layer and you basically try to manipulate this. But the world I come from, when I think of layered materials, I think of something like the cuprates. It's a layered crystal structure, but they're bulk single crystals, they're large, and you grow them in a furnace, not on a substrate. And they're typically very complicated because they have this layered structure, right? They're not like graphene. We have a well understood theoretical model for it, but they have a very weird or complex phase diagram, and the more we look at them, the more complicated they get. And so the material I want to tell you about today is somewhat like this, but it's a bit easier. It's a delaphosite, which again is a layered material, just if you know the cuprates, just similar to that. Has a layered crystal structure of conduction bands or conduction planes. But it's somewhat simpler because it's not as correlated. And it actually is a very good material to study of finite size confinement because it has a very long mean-free path, and that will become relevant. Okay, so if we start out with one of those materials or one of those structures, what they look like in our case, then we build things on a substrate, in this case sapphire. We interface our material with that because we don't want to like grow or make large structures from the material itself. But we use gold deposition on a substrate to contact our material. And then we build this 6-point structure here where we can pass current down the middle and we can basically measure voltage similar to what we've seen before and other things. And this is kind of like your graphene example, just that you have not one sheet, but you have 1,000 or 100,000 sheets of that. But because we start out with a bulk material, we can actually go one step further and we can also look at the out-of-plane conductance of this. So we can really make three-dimensional structures where we now pass our current down the sample, we go up in c-axis, we go back down, and with this we also can probe the interlayer transport between these materials. And what we do in this case is that we actually don't limit ourselves in the stacking number, but we actually limit ourselves in the in-plane dimension of these materials, okay? So we now here basically limit the material to like a few tens of micrometers, and that's actually on the order of the mean-free path of this. The way we do this is that we use focused ion beam machining. So we bombard our crystal with ions of different species. We can use gallium. This is the most common that some of you might know from preparation of TEM lamella. But we also have other species where we can use, for example, xenon, argon, nitrogen. There's a whole slew of ions that you can use nowadays. And that actually also helps us to identify what comes from actually cutting these materials with certain ions and what's actually intrinsic. Because if you use gallium, for example, then you can create a conduction layer on the surface simply by gallium implantation. It's a metal. But if you use xenon, then you have an inert gas and so forth. And then the structure that we do is very similar to what you do in transmission electron microscopy. You cut a lamella. It's just, in our case, much larger. And we can really tune this from hundreds of microns down to a few microns or structures of nanometric size. Then we interface it with a substrate that's basically produced in a clean room. And in the end, we structure it, and we really have control over the shape of this. So these are our lamella here. And then we really have control over the current path that we do in these structures to really look at exactly the property that we want to look at. In this case, maybe the anisotropy of the current or the resistivity. You can look at this in arbitrary shapes. If you say the material should be isotropic, you might want to test this in any direction, not just the high symmetry directions. You can also look at non-local effects. So you can pass a current down here and compare the voltage on this side and this side. And in the case where you have a surface transport-like phenomena, you would expect to see some voltage over here. But in the case where you don't have that, you would basically expect the voltage to be 0. And so that basically gives us this opportunity, this access to any, or to the current path to probe electrical transport in any direction of the material, and also to limit the size, maybe of the in-plane, maybe of the out-of-plane dimension of these materials when we do this. And as I said, this becomes important when we look at, for example, palladium cobaltate. Here's the crystal that I showed you in the beginning. It's layered. We're looking basically on top of the AB plane. But if we look into the crystal, then we see that we have this stacking of alternating palladium layers and cobalt oxide planes. What you find if you look at the electronic structure within this, so this is from ARPES, is that due to the crystal structure, which is hexagonal, you also find this hexagonal Fermi surface in this material. Okay. Now, the most interesting thing is that if you look at the resistivity in the plane, you already start out with 3.3 microohm centimeters at room temperature, which is something that most materials don't have, especially if you look at the cuprates, they don't even have that at low temperature. But then you go down to 8 nanoohm centimeters, and that's the equivalent to thinking of a mean free path of about 20 micrometers in this material. Okay? So if you look here, there's 100 micrometers, this is a sizable portion of this. And I just showed you we can make structures on the micrometer scale in these materials. So this is really a size that we can access. And we can immediately see this if we look at the in-plane resistivity of this material a bit better. So there's a different crystal. You can again see a little bit this hexagonal outline of this. And here our student Maya, she cut current paths into this material, which are all at different angles. So this looks a bit like what I showed you before, but they're actually all going in 10-degree steps. So this she called V0, and then we have V10, V20, V30, and this is basically because we have this hexagonal crystal structure. So if I go one step back, you basically say you provide a current path in this direction, and then you look at a current path in this direction. And what you can see is that at high temperatures where you have diffuse transport, so your mean free path is still on the order of a micrometer or so, all of those resistivity curves are exactly on top of each other. But if you go to low temperature, you start a split, and if you zoom in, you see that they actually split in a monotonic way. So V00 is the lowest, and then it monotonically goes up as you go up in angle. You can also look at what happens if you normalize it to the 30 degrees. Then you see at 100 Kelvin, it's all the same, and at low temperatures, it goes down. And this essentially comes from the fact that if you look at, again, the Fermi surface, all your VF are perpendicular to the Fermi surface. They point all in this direction. So if you now finite size confine this object, then if I cut a current path at 30 degrees, these states here will just scatter into the surface of my channel, okay? So here, basically, VF points along the direction of the current path, and then this one, VF just points into the walls. So you get enhanced surface scattering in the plane, and you can really think of this material similar to a billiard table. And basically here, you're just shooting your ball away straight into the wall, and so it has a much higher resistivity to end up on the other side. Okay. We can also see this effect if we look at magnetic field dependence. And so the way we did this was now we look at the C-axis resistivity. We're not looking at the in-plane resistivity anymore, but we're looking at the interlayer transport. But we're looking at the same effect. We take a bar here in current path. This is the C-axis going straight up, and we look at its resistivity at low temperature. at different widths or dimensions of this channel. So now you have a block where you confine the material in the plane, okay? So as we showed before, we would expect that the resistivity would go up the smaller we make the channel, and that's the case. If we go from 5.5 micron to 1.7, our resistivity in zero field goes up. But as we apply magnetic field, first we have a little bit of a downturn and then a very abrupt downturn, and that actually comes from the fact that what we do in magnetic field is we now start to spiral this. In a semi-classical picture, we start to spiral this by Lorentz force, and once this orbit becomes actually smaller than the smallest dimension of our material, we actually get a drop in resistivity, and eventually we recover the bulk properties of our material. Okay? So that essentially gives us a tuning knob to say we go between finite size confinement and a bulk single crystal, and the tuning knob is magnetic field. A different way how we can tune magnetic field is if we now say, okay, we can also turn this magnetic field. Because the point is all our electrons live in the plane and they want to spiral in the plane. And so the question is, what is the strength of magnetic field perpendicular to this plane? So what is the Lorentz force in this plane? And this we can tune basically by a cosinusoidal dependence if we turn the magnetic field in a different direction. And now we look at what happens to the resistivity, or in this case, the second derivative with magnetic field of the resistivity, as we turn the magnetic field. And what we get are two regimes. They're again split by these points here. So they're now minima here in these curves, and they're represented by this dashed line. So this is the transition between bulk and surface or mesoscopic scale behavior. And what you can see is similar to what we saw before in this manganese bismuth telluride is magnetic quantum oscillations in this regime. So this is the regime where we are in the bulk limit. We basically only spiral in this material. The electrons don't know anything about the surface. And what we see is the bulk behavior, and that is magnetic quantum oscillations. They're 1/b periodic. But what we get here is also a type of oscillations, but they're not 1/b periodic. They're actually B periodic. And the reason why they're B periodic, or what happens there is that these electrons see the surface, as I told you. And so these oscillations actually come from the fact that you have standing waves in your material. If we're not thinking about a particle anymore, but now we're thinking of a wave solution, we actually have a standing wave because the mean free path is so long that the electron doesn't scatter within the plane. And then that wave needs to go from one level or one palladium layer to the next. And the way it does so is either constructively or destructively, depending on what the phase between these two planes is. And you set this phase by the magnetic field again. So as you tune the magnetic field, you tune the phase between two adjacent palladium layers or of these standing waves. And that basically leads to a B-periodic oscillation that is similar to a Aharonov-Bohm effect. So you could think of the size of the material and the spacing of two palladium layers as kind of a Aharonov-Bohm type ring, where you actually get interference effects of the electrons going from one level to the next. Okay, in a hand-waving picture. Okay, you can also see this at some intermediate angles. So if we look at the angles here, you can again see this B star, where we basically switch from this angle here, or this field scale here, where our electrons are still seeing the box, to the bulk oscillations. And we basically can really use magnetic field as a tuning knob to actually switch between these two states. These two states also have very different effects in terms of, or properties in terms of transport. So these mesoscopic term in low field, as I told you, we can see up to about 20 micrometers because they're basically in plane mean free path. And that comes from the fact that you're only probing these VF states on these flat regions of the Fermi surface. But these bulk oscillations up here, they actually have a much lower mean free path, because what you do here is you really look at a K-space property and you circle and you basically measure the average of this Fermi surface, and you also need to take the corners into account, and that actually gives you some mixing between these two parts, and that actually reduces the mean free path. But the other thing is how they're massively different is that, as we've seen before, the amplitude dependence of these oscillations from the bulk oscillations gives you something like the mean free path. So this gives you the renormalization of your electrons or the renormalized mass, and that drops very quickly and typically falls off at about 4 Kelvin. Typically, you don't see these oscillations above 8 Kelvin unless you have something like ultralight carriers like in graphene. But these mesoscopic oscillations, you can really see up to much higher temperatures. You can see those up to about 60 Kelvin, and that comes from the fact that these, this mean free path basically is, or the temperature dependence of this mean free path is pretty flat, and you basically see those all the way up to the point where you, your energy scale becomes on the order of your Fermi surface warping, so you can't actually distinguish between which part of the Fermi surface these come from anymore. And then you basically start to lose those once you actually have enough temperature smearing to really refine your Fermi surface. So there you can already see that you really have two very, very different effects. And again, the reason why we can observe that is because we actually have this property to really look at in-plane confinement versus z-axis confinement of these materials. Okay? Okay, so at this point where we're talking about in-plane confinement, my abstract said I'm going to talk about a twist. And one way how we do twisting, and that was what I thought about telling you, is we can take materials now and actually finite size confine them, and then because of the finite size confinement, we can actually also turn them, which you can't do in a bulk single or a large single crystal because they would break due to the stress of the surface. But we recently actually came across a different property which was a bit more of a twist in the project. When we wanted to look at the finite size confinement in the plane and we make these lamella structures, we actually realized, oh, if we take a different material, in this case strontium ruthenate or cuprate, they actually turned transparent. And that was a bit of a twist in that story, so I'm going to tell you a little bit about that rather than twisting uranium, ruthenium to silicon do. So let's think about what we need if we want to have a transparent metal. And this might also be maybe more interesting for the community here. If you think about lasers, if you want to work on that. We need to bring together a material that's transparent with something that's highly conductive. Okay? And typically the way we do this is we can use a substrate, sapphire, and then we do thin film deposition. So we do 10, 20 nanometers, you do gold on sapphire, and it's still somewhat transparent. But as soon as you get thicker, you actually run into an issue because your material starts to reflect. And that's typically what we get up here. And so this limits us to few nanometers of these films, and that basically gives you a high resistance. Now, one thing that you can do if you look at, well, what actually can I do to a material in order to make it transparent is I can play with the carrier density. And so that's how people basically use semiconductors and ITO, for example, to actually tune this and to come up with ways of material to really be transparent at much higher thicknesses, so 100 nanometers or so. Then you can use the effective mass to tune this. Now you go back to the low or the smaller thickness, and you basically tune your effective mass in correlated oxides to, again, produce something that is a transparent metal. But what we actually found in this material is something, if you think of a layered material, you have two kinds of conductivity. You have the interlayer conductivity, and you have the in-plane conductivity. And I just showed you that in the plane of palladium cobaltate, we're basically ballistic. We have a mean free path of 20 micrometers, very long, right? But out of plane, when you look at the interlayer hopping, that's basically very different, and the conductivity here in this case, strontium ruthenate, is about 100 times lower. So what we actually get in these materials are two different plasma frequencies. Okay, so we can see this here, room temperature. We get this drop between rho A, B of microohm centimeters to milliohm centimeters in C. And so what we can do is we can think of an experiment or of our slab of material where we have conduction planes here with a plasma frequency that basically leads to reflection, similar to gold. But if we look at the interlayer transport, we basically get a conductivity that's similar to these semiconductors, so ITO. And so they basically should be transparent. Okay? And if we actually do this and we look at our lamellas, and this is where the twist came, this is the lamella of strontium ruthenate where we're trying to look at finite size confinement of transport. But we actually realized, hold on, why is that transparent? And it is actually exactly because of this phenomena that we have this anisotropy in transport. So what we do here is we have an aluminum film on sapphire. We structured this. This was still done at EPFL, so that's why we have the EPFL logo structured into that. And then we place 2 lamella that are about a micrometer thick on top of this, and we back illuminate it. So we have white light coming from the back. And then we place a second one on top, and we can move this second one. We can turn this by 90 degrees. And what you see is you get transmission through one lamella, but not through the other. And the reason for that is because you only have transmission in one polarization. You only get transmission in C-axis. They basically polarize themselves. So you get transmission on micrometer scale rather than on 10 or 100 nanometers in the metal. And at the same time, you get this polarization effect. And all of that comes from the fact that you basically localize your electrons in C-axis, but you basically have good conduction in the plane. Our colleagues in Boston then basically measured the polarization capability of this. And they could really show that this is almost wavelength independent over the range of visible light. And we actually get transmission of more than 80%. So if you compare that to what you get in commercial filters, typically also Attaj's group, they told us that basically their commercial filters were probably the limiting case, and they couldn't really tell how good it was actually as a polarizer. But this is quite convincing that we really get high values for this. And so what we found in that then is that you basically now have a transparent conductor that is highly polarizing, that is just a showcase of what happens if you basically finite size limit a layered material, and that you can actually get a differentiation between the optical conductivity in the C-axis and a very good metal in the plane, all the way to the fact that you can actually do this in high temperature superconductors. So basically you can now think of a material that is a transparent metal with basically no electrical resistance. And that's another technique more tailored to the application or showcasing what can be done in this case. Maybe that's also more or I thought maybe this is interesting for this part of the community, because the theme and the question that James asked in the beginning was, well, what can we do as a new starting point? And then people were talking about, okay, you build cavities, okay? So here we basically show that you can think of cavities in a very different way. We can actually not grow a material, but you can now think of bulk single crystals. We shape them exactly into the dimension that's necessary, and you can use the material itself maybe as a cavity for future experiments. Okay, and with that, I would like to thank you for your attention.